Problem number 1 says, using the figure above and knowing that the charge on Q2 is 2.5 microcoulombs, let's answer these questions. All right, so what I'm going to do, just for the sake of talking about it, let's go ahead and say that we know that that charge is 2.5 microcoulomb, which is the same thing as 2.5 times 10 to the negative 6 coulomb. The first question says, determine the charge on Q1. Now, a couple of things. Q2 has field lines leaving itself, so we know that is a positive value. Q1 has lines going in, so we know that Q1 right now is negative. So I'm going to write that as a negative value. And here's the thing. If we don't necessarily remember, the number of lines we draw is arbitrary, but because we have two charges that are in the general vicinity and we know one of them, we know that the ratio of lines in one charge equals the ratio of lines in the other charge. So I'm going to count. There's 1, 2, 3, 4 lines for this guy. So there's 4 lines right there. I'll just write that down just for the sake of us looking at it. And let's look at all the lines going through Q1. I'm going to put a little tick mark there so I know that's where I started. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 16 lines in Q2. That's going to be Q1. Q2 is one we know. Well, if there's 4 lines in that one and 16 lines in here, there's 4 times the lines in Q1, which means Q1 better be 4 times that value. So 4 times 2.5 would be 10, or 1 times 10 to the negative 5th coulombs. But because lines are going in, it's negative. So I'm going to write that's negative 1 times 10 to the negative 5th coulombs, or negative 10 microcoulomb. I'll take either one. So 2.5 times the 4 is going to give us the 10 microcoulombs. All right, next question says, draw a vector to represent the electric field at point P. So these are not actual fields. They're referred to as what's called the field line. And so they basically show the general flow. If I put a positive charge right there, a little positive charge right there, and let it go, it would follow that path if I let it go. If I put the positive charge right there, it would follow that path, so on and so forth. But the actual field at that spot is a vector quantity. So I'll do this in red so you can see it. The field starts there, points tangent. So the key idea is that it's tangent and that it points in the same direction. So see how it's kind of going kind of down and to the left? I want to stay that same idea. So down to the left, but it's tangent. So the best I can draw, I'm going to draw a little arrow right there to represent the electric field at point P. It should be tangent, and it should be in the general direction at that point in time. So as long as you do that pretty close, you'll get credit for that. So we did part B. So check for A, check for B. Part C, which point has the strongest electric field? So if I take a look, we know that the strongest electric field happens when the field lines are the closest. So if it happens when they're the closest, let's look. We're looking at A, B, or C. A is right there, B is right there, and C is right there. It looks like the field lines are closest at A, so I'll say A. If I was to rank them, I would say A is the greatest field, followed by B, followed by C. Because B, the lines are pretty close together, but not as close as they are for A, and then C is not really near any lines. And so we would expect A to have the strongest field right there. So question number 2 says we have a 2-kilogram dumbbell. It's given enough electrons, so we've transferred enough electrons for it to float in a uniform electric field with a strength of 2.5 times 10 to the negative 6 newtons per coulomb on Earth. And then in parentheses, it says, assume gravity does matter since the dumbbell has significant mass. So in a lot of these problems we've been working, we've really kind of neglected gravity because we've been talking about protons and electrons, which have insignificant mass. So the weight of a proton, the weight of an electron is really, really small compared to the overall charge on it, relatively speaking. But because we're talking about a 2-kilogram dumbbell, that's pretty large, and so we will have gravity. So we're on Earth. It says it floats. Well, if it's floating, it's probably just hanging out right there. So if I have a dumbbell, terrible picture, but if I have a dumbbell and it's just floating right there, what we could probably do is say this, the net force is 0. Well, we know gravity always acts straight down. So Fg has to act straight down. So if I'm talking about a free body diagram, I'll come down here and draw a free body diagram. We have Fg acting straight down. Well, in order for it to float, we would have to have something canceling out gravity. So I'm expecting that is the electric force. Okay, so Fe would have to be acting up. So Fe acts up on the electron. All right, we know that an electron is negative. Okay, it's negative. What does that mean? We know that negatives go opposite the E field, the electric field. So if it's being forced up, what that actually means is that the electric field is pointing down. And it does say it's a uniform field. So the field lines are all evenly spaced and pointing in the same direction. So the electric field is actually pointing down in order for the electrons to go up, opposite the electric field. So the answer to part A is down. The electric field must be pointing down in order for it to flow. Now it says, how many electrons does the dumbbell have in order for this to happen? So I'm going to still start with our free body diagram and say sum of the forces is equal to zero. We know that Fg down has to equal the electric force up. Well, what is Fg? Fg is mg equals the electric force up. Well, the electric force, remember our friend, when we're in a uniform field of E, the relationship of E to F, Fe is E equals Fe over Q, or Fe is equal to QE. So I'm going to say that it's the charge times the electric field. So the only thing we don't know is Q. So the electric field, the charge, I should say, Q, is equal to mg divided by the electric field. So the mass is 2 kilograms. By adding electrons, are you adding mass? Yes, but that's like adding lint to your pocket. It's not really changing the overall mass of the 2 kilogram dumbbell, times 9.8 meters per second squared. And then the electric field is 2.5 times 10 to the 6th newtons per coulomb. All right, so if I do that really quickly, I get 2 times 9.8 divided by 2.5 times 10 to the 10 to the 6th, and I get 7.84 times 10 to the negative 6, and that should be coulombs, because a kilogram times a meter per second squared, that is a newton. The newton and newton cancels, which is just leaving me coulombs. And so this is 7.84 microcoulombs, all right, is the overall charge. All right, so let's keep that in mind. That's overall charge. And then it says, but how many electrons? We know that one electron has a charge of 1.6 times 10 to the negative 19th coulomb. So you have to have a lot of them to get to that value, or that value, the same thing. So what I'm going to do is I'm going to start with 7.84 times 10 to the negative 6 coulomb over 1. We know that one electron has the charge of 1.6 times 10 to the negative 19th coulomb. So coulombs will cancel. So if I take that value and divide by 1.6 times 10 to the negative 19th, I get 4.9 times 10 to the 13 electrons. Move it over a little bit. And so that's how many electrons I would have to deposit on the dumbbell in order for a 2 kilogram dumbbell to float on Earth in a uniform electric field. So we could actually cause this 2 kilogram dumbbell just to levitate, which is kind of awesome. But we would need that many electrons added to it.